Welcome back. This is the fifth video in the series of lectures on special theory of relativity. In this video, I will be describing the velocity addition theorem or the transformation of velocity according to Lorentz transformation. There is a need for a different velocity transformation equation since we already saw in the previous videos that the Galilean transformation will yield different values for the speed of light for different inertial observers who are in relative motion with respect to each other. But we also saw from Michelson-Morley experiment that this is not the case, that the speed of light is in free space is supposed to be a constant and is independent of the motion of the frame or the observer or even the motion of the source. In order to derive the velocity addition theorem, let's consider a particle moving with a velocity u dash with respect to the frame s dash. The frame s dash itself is moving with the velocity v along the positive x-axis with respect to s. Let the components of the velocity of the particle along the x dash, y dash and z dash axis be ux dash, uy dash and uz dash respectively. Now let's consider the inverse Lorentz transformation. So from the inverse Lorentz transformation, we have x is equal to x dash plus vt dash divided by square root of 1 minus v squared by c squared. Y is equal to y dash, z is equal to z dash and t is equal to t dash plus v by c squared times x dash divided by square root of 1 minus v squared by c squared. Now if we take the differential of these terms, we obtain dx is equal to k times dx dash plus v times dt dash, where k is equal to 1 by square root of 1 minus v squared by c squared. Similarly, dy will be equal to dy dash, dz will be equal to dz dash, while dt will be equal to k times dt dash plus v by c squared times dx dash. Now, if we consider the frame S, the component of the velocity of the particle would be ux equal to dx by dt along x-axis, uy equal to dy by dt along y-axis and uz equal to dz by dt along the z-axis. In order to calculate ux, we substitute the value of dx and dt from the previous slide and obtain ux is equal to k times dx dash plus v into dt dash divided by k times dt dash plus v by c squared times dx dash. Cancelling k, we obtain ux is equal to dx dash plus v times dt dash divided by dt dash plus v by c squared times dx dash. Taking dt dash as a common factor in the denominator, we obtain ux is equal to dx dash plus v times dt dash divided by dt dash times 1 plus v by c squared times dx dash by dt dash. Now, if we divide the numerator and denominator by dt dash, we can solve for ux as ux is equal to dx dash by dt dash, which is nothing but ux dash plus v divided by 1 plus v by c squared times dx dash by dt dash, which is nothing but ux dash. Hence, we get ux is equal to ux dash plus v divided by 1 plus v by c squared times ux dash. Similarly, by substituting for dy and dt, we can show that uy is equal to uy dash divided by k times 1 plus v by c squared ux dash and uz is equal to ux dash divided by k times 1 plus v by c squared ux dash. So in this slide, we see that the normal transformation of the velocities can be written as ux dash is equal to ux minus v divided by 1 minus v by c squared times ux, uy dash is equal to uy divided by k times 1 minus v by c squared ux and uz dash is equal to uz divided by k times 1 minus v by c squared ux. Note that the normal transformation are the transformations which enable us to transform the velocity from the s frame to the s dash frame. Now, in order to work out the inverse transformation for velocities, all we need to do is change the sign of the velocity v, and therefore we obtain ux is equal to ux dash plus v divided by 1 plus v by c squared ux dash, and uy is equal to uy dash divided by k times 1 plus v by c squared ux dash, and finally uz equal to uz dash divided by k times 1 plus v by c squared ux dash. Thus, we see that these transformation equations are different from the Galilean transformation equations for velocities. I'll look at some consequence of the velocity addition theorem in this slide. First of all, note that for the x component of the velocity in the normal transformations, that is ux dash, or in the inverse transformation, that is expression for ux, there is no occurrence of the factor k. However, when you consider the y component of the velocity uy dash and uz dash in the normal transformations and uy and uz in the inverse transformation, we note that the factor k occurs in the denominator. A more important observation to make is that if you observe, you note that even though the frame s dash has a velocity only along the x-axis, the component of the velocity of an object along the y and z axis, that is uy and uz or uy dash and uz dash, actually changes. Why does this happen? Think about it. A little thought should tell you that this is because the velocity along the y-axis dy by dt or the velocity along the z-axis dz by dt depends both on dy and dt and dz and dt respectively. That is, even though there is no change along the y direction for the length, that is no change in dy or no length contraction effect perpendicular to the direction of motion of the frame, similarly no change in dz, there will always be time dilation effect, and hence the velocity component along the y and z axis also changes. In other words, we should remember that the length contraction happens only in the direction of motion of the frame, while time dilation on the other hand is independent of the direction of motion of the frame. The second important point I would like to make is to show that the velocity transformation equations or velocity addition theorem is consistent with the postulate of relativity. Now, if you consider a photon moving with a speed c with respect to the frame s along the positive x-axis, then for an observer s dash who is moving along the positive x-axis with a speed v equal to, let us say, half the speed of light, that is v equal to c by 2, then what is the speed of the photon for the observer in s dash? Let's work this out. Now, using the normal transformations, ux dash is equal to ux minus v divided by 1 minus v by c squared ux. Therefore, I get, substituting for v, ux dash is equal to c minus c by 2 divided by 1 minus c by 2 c squared times c, or ux dash is equal to c by 2 divided by half, which is equal to c. That means the speed of the photon as measured by the moving observer in frame s dash is also c along the x-axis, and of course the speed of the photon was c with respect to the frame s. Hence, we see that this is consistent with the postulate of the special theory of relativity and is the correct, the velocity transformation equations mentioned here are the correct transformation equations. Thus, we come to the end of video number 5 in this series of lectures on special theory of relativity. In this video, we looked at the velocity transformation equations or velocity addition theorem as per STR. We noted that these transformation equations are compatible with the second postulate of relativity, namely that the speed of light is independent of the motion of the observer. Of course, it is also independent of the speed of the object which emits the light itself. In the next video, we will look at one of the major results of special theory of relativity, namely the variation of mass with speed of an object. I thank all of you for watching this video and hope that it has been useful to you. I once again acknowledge Robert Resnick, the author of the book Introduction to Special Relativity, Wiley Student Edition 2014. I urge all of you to read this textbook.